Hey, what's up guys? So everyone knows that I love LEDs. I've made a ton of videos on LED based projects, how to drive and control LEDs. So it was just a matter of time before I made a video on addressable LEDs, specifically the WS2812 LED with the built-in driver. So in this video, I'm going to show you how to work with these LEDs from a standard Arduino Uno platform. So we're using the 8-bit microcontroller, the ATmega328. So the timing was really tricky to get right, and I'm going to show you the code that I wrote to run these LEDs. So no special libraries or anything like that. We're working straight out of the standard Arduino IDE. So let me show you what I came up with over here. Okay, so a couple years back when these LEDs first came out, I picked up a few of these panels here that you can actually break off the LEDs out of the panel and then use them for whatever. So they're not actually electrically connected in the panel, and that's why you can see here on the back I've got all of these LEDs hooked in series with each other. So I'm applying 5 volts and ground to every single LED here. And then I've got a huge 1000 microfarad capacitor here connected right across 5 volts and ground. And then right off of digital pin 8 of the microcontroller, and by the way, this is a little cheater board here that's Arduino compatible. It's got the ATmega328P-PU running at 16 megahertz. And if you want more information about this board, check out the description below. So right off of that microcontroller, pin 8 feeds the first WS2812, and then that data out pin from the first LED is connected to the data in of the second LED, and then they're just connected in series like that all the way through 45 LEDs here. And I got a little diffuser here. It makes a nice effect with that animation. And by the way, these LEDs have been out for a few years now, so there's tons of libraries out there that you can go and download and get up and running with these LEDs pretty quickly. Adafruit calls these the NeoPixel, so you can grab the NeoPixel library and you'll be good to go. But what I did here was I wrote my own code. There's no libraries. It's just a simple function that loops through and controls these LEDs. So let's jump over to the datasheet here. I want to show you how these LEDs actually work. Oh, but first let me show you the website here, World Semi, and this is the company that actually makes these LEDs. And you can see here that they've got a lot of different types of LEDs. And in case you're not familiar with these, they're really cool. They're in a standard 50 by 50 LED package, but they actually have the controller and driver built right in. So basically we load it up with data and then it will control the LED itself. So we give it 3 bytes for the red, green, blue values, and then the LED itself takes over and will control the LED via PWM. So it's really cool. You just give it the values, get in, get out, and then the LED itself controls the LED. So it's really amazing. And if you want to use your own RGB LEDs, they sell the driver ICs separately. So that's kind of cool. And you see these all over the place. They're in LED strips and all over the place. I just saw these at the mall the other day. It's kind of crazy. But really cool LED. So let me jump over to the datasheet here. And I'm pretty sure I've got the WS2812B version. I'm not 100% on that, so if any of you out there test my code, let me know if it works. And also, I only have 45 LEDs here, so one of the things I want to do is test this with like 1,000 LEDs to make sure that the timing works across a large number of LEDs, which I'm pretty sure it would. But if any of you do test that, let me know if it works. So anyway, this is the LED. You've got four pins on the LED. We're running it at 5 volts across VDD and VSS, and then data D in is our data in pin right off of the microcontroller, and then the D out pin goes to the next LED. And we'll talk more about that here as we move through this. I'm just going to fly down to how you actually write data to the LED. So it's kind of crazy. We only have 1 pin controlling the LED, so how do we get data into it? It's not like we have a clock pin and a data pin, just 1 pin for both. So here's how the data is fed into the LEDs. We've got 8 bits for the green, 8 bits for the red, 8 bits for the blue, and so those correspond to the brightnesses of each green, red, blue LED in the package. So, you know, it is 8 bits, so we've got 0 to 255 for the brightness. So you combine those brightness values for the RGB and you'll get any color you want. So you're mixing colors there. So you load up the first LED with the 24 bits, and then you keep sending bits out, and the next 24 just passes along on to the second LED, send out another stream of 24 bits, you get the next LED, and so on. So that's kind of how it works. And then when you look at how you actually determine what's a 0 and a 1 in those bits, you come up here and they show you here in this sequence chart how you're actually doing it. So if you need to send a 0, you start out high for some period of time, then low. If you need to send a 1, you're high a little bit longer than you were for a 0, and then low for a little shorter period of time. And then the LED is actually smart enough to know that, oh, when I see a short pulse like that, it must be a 0. If it's a longer pulse, it's a 1. And when you look at these timings, I mean, it's incredible. So for a 0, we're only high for 0.4 microseconds. For a 1, we're high for 0.8 microseconds. So that's the difference there between a 0 and a 1. So it's really crazy. So I mean, when you look at your Arduino code, you're running delays in the milliseconds, or even a delay microseconds is, you know, just, it's a full microsecond. So we need to get delays down to 0.4 microseconds. So that's kind of the magic in the code here. So let's jump over to the code and I'll show you exactly how that all works. Okay, so before we do that, I just want to show you how easy it is to actually run my code here. So we're just going to drive the first LED. So here's the function here. So we've got 4 values. The first value is the LED number in the actual connection. You know, if you've got all these connected in series, the first LED that you're connected to would be LED 0, and then so on. And then the next 3 values here would be the brightness values for the RGB. So let's just make the red LED full brightness at 255, and I'm going to go ahead and upload that real quick. And then we should see this. Oh, there it is. The first LED there goes to red. And then I'll just go to the next G here and make that 255. And now we should see that. You know what? I should have just copied and pasted this out. There's green. And then finally, let's just do it. Make the last one there, 255, and then we'd have blue there. So what I'm getting at here, though, is that this function is all you need to control all of the LEDs, and you can have for loops around this and mix all kinds of colors and fade it in and out. And you saw that test animation I wrote using just this simple function. So when we get into the code and how it all works, you'll kind of see how this works and how you can actually just update the entire panel at once, because this function just updates a single LED, and as soon as you call this function, it's actually updating the entire panel here. So if you wanted to just, you know, update all of the LEDs at one time, make them all blue, what you could do is update the LED array. Let me just do that for you real quick here. Okay, so this code here updates all of the LEDs at one time. So this is kind of cool. Basically what we're doing here, and we'll talk more about this in a second here, is we're going through and updating every third byte in the RGB array here. So that's why you see this I is equal to I plus 3, and you see 135 because that's the size of the entire array holding all of the bytes in the LED panel here, because we do have 45 LEDs, but each LED has 3 bytes. So that's why we have 135 bytes total. So we update every third byte in that array and set it to 255. And then to update them all at once, we call this same function, but this time the LED value is set to -1. And you'll see why in a second here in the function. But anyway, that was just an example of how to work with this code here. So it's really super lightweight. In fact, if we look at the let's see how big the code is actually at here. So you can see that Sketch is like, I don't know, like 1100 bytes. The global variable is 144, and that's actually for pretty much the 135 bytes needed for the entire panel. And we'll see more of that here in a second. But anyway, you can see it's extremely lightweight. So let's start right up at the top and do a quick walkthrough of this code. I also have the scope hooked up over here, so we're going to see the timing and how it all works, and we'll take it from there. So right up here at the top, here's our pin that is hooked up to the LED. So we're using digital pin 8, and only digital pin 8 works at this time. I think I can make the other pins work as well, but haven't had a chance yet to test all of that out. So only digital pin 8 works. We have 45 LEDs hooked up in the panel, and then here's the array of bytes for the RGB data, and that's basically just 45 times 3, because we have an RGB byte for each LED. Okay, define the function there, and then we set that pin to an output, and then we jump down to the function itself, and there's not a whole lot here. So let's walk through and see exactly how this works. So we've got a couple local variables, which I'll explain in a second, and then here is where we do a quick check to see if the LED value coming in here is greater than 0, and if it is, map the red, green, blue bytes to the bytes in the RGB array. So you can see we're just doing times 3 plus 1 for the red, times 3 plus 2 for the blue. Okay. And then of course, if it's -1, skip this whole thing, because we've already set those bytes, like I was showing you before here. We've already set the bytes, and we just want to update the entire panel. So that's what that does there. Then we kill the interrupts, and then we grab a snapshot. And the reason we kill these interrupts is just so nothing interrupts us while we're sending out these bits, because if anything gets screwed up, it'll knock us out, screw up the timing, and we'll get weird writing to the LEDs, and it'll look like it could flicker, it could have the wrong color or whatever. So anyway, I just kill the interrupts there to be safe. Then we grab a snapshot of what port B is currently set at. So if you're using the other pins in port B, you can continue to do that, and I don't want this function here to screw up anything that you had already set on port B. So port B is what digital pin 8 is connected to, and in case this looks confusing to you, I just did a video on direct port manipulation that would explain exactly how I'm doing this and setting the digital pin 8 as fast as possible, high and low. So anyway, we grab a snapshot of port B, and that'll make sense here in a second as well. Then I need a fast way to write digital pin 8 high, and that's why I'm just setting this variable here to the entire port B, ORed with 1, because digital pin 8 is connected to the first bit of port B. So I'm ORing it with 1, which would force that first pin, digital pin 8, high. Okay, then our bit stream is equal to the number of LEDs times 3, so that when we're looping through all of the bytes in that array, we have 135 bytes in the 45 LED panel here. So that's what brings us to this for loop, and this for loop is where all of the magic happens. Okay, and this is where we do all of that timing. And let me start off right at the top here. So I'm actually going to hook the scope up so we can see this stuff. Okay, so in order to really test this code out, let's start off by writing the first LED all zeros. So you can see here in RGB update, we're setting the first LED with an RGB value of 0, okay? And we should be able to watch this on the scope over here and make sure that the timing all looks right, and we'll walk through this for loop and see how it's actually determining if the bits are high and low. So over in the datasheet here, we'll go down here to the bit stream, and it's expecting the first bit to be bit 7 of the green byte. Okay, so let's go to the for loop here, and you can see that the first thing we do is set digital pin 8 high. Okay, we already know how to set that pin high. We've grabbed that, so we can set it very quickly here by just setting the entire port B equal to WS2812 pin high. Okay, and so we set that high no matter what. That's the first thing we do. And then I've got an explanation here of what I'm doing next. Now the next piece of code here, this port B equals the RGB value ANDed with this, and then double AND with that, or with the existing port. Seems confusing, but basically what we're doing here is checking bit 7 of the green byte for the first LED. Okay, so you can see here that we're going through it. So I is equal to 0, and so like let's just start off with it. It would be that first LED's green byte, okay, that's coming through here. So what we're doing is grabbing, ANDing it with B1 followed by 7 zeros. So we want to just strip off everything else that's in this green byte. We're only interested in bit 7. So what we're left with, if it's a 1, would be 1 followed by 7 zeros. If it's a 0, it would just be all zeros. Okay, and then we do a double AND here with a B1 followed by 7 zeros. So the outcome of this whole thing here would either be just a 1 or a 0, and that's all we want. If it's a 1, we OR it with the existing port, which would set port B high. So it already is high, but we just set it again high, so it just remains high. Okay, and that's how we get this critical timing here to work. If it was a 0, the outcome of this, then it would immediately force that pin low, which is what it's doing here on the scope. So you can see that it goes high, and I've got the width of this set to 400 nanoseconds, which is the requirement of the data sheet here. So when you see here, for a 0 code, the high time must be 4.4 microseconds or 400 nanoseconds. And one of the things I'm trying to do here with my code is just keep it symmetric. So for a 0 code, I want the high time to be 400, the low time to be 800. For a 1 code, I want the high time to be 800, the low time to be 400 nanoseconds. Okay, hopefully I said that right. So anyway, you can see here though that we've got that high time working for a low bit. In fact, just while I've got it, actually, I don't want to do that quite yet. So you can see that this works really fast, and we're actually getting it. So we're able to, with this simple line of code here, we're getting it to write high and then immediate low, and that happens within 400 nanoseconds. So I'm very lucky that happens to work out perfectly for this timing. Okay, now this might look a little confusing, but you might have seen this from some of my other videos, and this is inline assembler here. And these are NOPs, or no operations. So this basically lets us do the smallest amount of delay as possible. We can't use delay microseconds or delays or anything like that. These are actually delaying clock cycles themselves. So I kind of tuned this out to get this timing just right. So what I'm doing is kind of loading up a few of these NOPs in a row here to keep that pin low here. And then I force the pin low here by setting port B equal to the existing port. Now, when I came into this function, digital pin 8 was low, okay? So when I set it to the existing port, it forces it low. And the reason for this is because if the outcome of this was to keep it high, this would then keep it high even longer here and then force it low. Okay, so that's the idea. This is to keep that hot pin high for the remaining 800 nanoseconds. Okay, and then we force it low, and you'll see that again here. I'm going to flip the value around to 255 so that we see what a high byte or a high bit would look like here. And then we keep it low the remaining period of time for the remaining 800 nanoseconds or 400 nanoseconds here, and this is all critical tuning here to get this all right. So let's measure out what our low time is here. Okay, so I said 800 nanoseconds. So I'm going to move that over, and you can see that it's perfectly set to 800 nanoseconds there. So that looks great. So that is what a low bit would look like. And then what it does is it just moves on through that entire byte. So we're actually just going through bytes. So you see we've got the RGB value here in the array, and this would be 0 to 135. So we're actually just looping through all the bytes, and in this for loop we're going through the bits in that byte. So we're starting with bit 7. We do the same exact thing for bit 6. We set it high again, and then we do the check, but this time we're looking at bit 6. Okay, so the outcome of this would either be a 1 or a 0. Then we do bit 5, then we do bit 4, bit 3, bit 2, bit 1, finally bit 0, and then it repeats. Okay, so it does that and loops through all 135 bytes here. Now, one thing you might notice is that with this one, the final bit in the byte, I needed to add another NOP here right after setting the pin high, and that's because I think this operation here is much quicker. So I actually had to delay this a little bit longer to keep it high to maintain, the proper 400 nanoseconds there. So I had to add in another NOP for this last one, and I also had to get rid of the NOPs here right after setting the pin low. And that's because, so that would normally go right here after setting the port low, or the pin low, sorry. And that's because after this point in the code, it loops back up and does the check on I here. And that time alone here is almost perfectly timed for what this is here, those knobs. Okay, so hopefully that all makes sense, and I've got that documented out here, so hopefully it does. But anyway, let's now set. Actually, before I do that, let me show you what that final bit looks like. So we see 1, 2, 3, 4, 5, 6, 7, and 8. So you can't even tell that that's bit 8 there. The timing, it just works out beautifully, and it just keeps going, and you can't tell a difference that that's the final bit in that byte. So now let's set that value RG. I'm going to set it because it's green first. I'm going to set the green value high. Okay, so immediately, so you see that the LED is green over there. I'm going to start back over at the beginning, and now let's look at this timing here. Okay, so again, I'll move that over a little bit. Okay, so remember that now we have to be high for 800 nanoseconds and low for 400 nanoseconds. And you can see that we are high. So the code is doing its job. So right here, it's actually keeping that pin high for this amount of time. So it keeps it high. It has some NOPs in there to keep it high for the remaining 800 nanoseconds. And then boom, it drops it out right here and then keeps it off for the remaining 400 nanoseconds down there. Okay, so I'll measure that out too. Let me show you that. Okay, so you can see we've got a perfect 400 nanoseconds there for the low portion of the high bit. And for this, we'll be able to see that last bit pretty easily because then the next value, the next byte, would all be zeros. So you can see here that, I'm trying to zoom in on it a little bit there. Okay, so you can see that this is the last bit. This would be bit 0 in the green byte there. And I'm just going to move that over a little bit and show you that we are indeed still low for 400 nanoseconds. And then I'm going to just pull that out to about 800 there and show you that we're still high. So we're still able to maintain the 800 nanoseconds for the high portion of that bit as well. Okay, and that's pretty much it. That's the code. So it's extremely lightweight. I probably made this video a lot longer than it had to be, but anyway, I think that covers everything I wanted to show you. I wanted to show you the timing, how it all works. And by the way, just a little side note here. This code looks simple, okay? And it is simple. It's very simple. But it took me a long time to actually get this all to work. My first idea with this was to use a timer interrupt that would interrupt me every 1.25 microseconds, which is actually the full period of one of these bits, okay? and or I think it's 1.2 microseconds. And I wanted to interrupt myself and then do the high bit, low bit, kind of, or the high portion of the bit, low portion of the byte, kind of do all that in a timer interrupt that just ran, and it was always checking the full RGB array. But it turned out that interrupt, pulling in and out of that interrupt, took like 2 microseconds, so that wasn't gonna work. Then I tried doing running these LEDs from off of the SPI port, and I was going to run that SPI port at 8 megahertz and then keep the bits that I'm streaming out either high or low to get this timing all to work out. But that didn't quite work out because there is a time delay between the byte writes out of the SPI port, and I was trying to optimize that, and I went down that road. And then I figured, all right, well, let's just get back to bit banging it like this. And this is not only more optimal from a memory standpoint, but it's also much faster and just works. It's a lot lightweight. So anyway, I know I'm kind of rambling here a little bit, but anyway, that is the code. So I'll have all this available in the description, so you could just copy this. You could copy this function right into your code, and bam, you'll be up and running with these LEDs in no time. So again, let me know in the comments below if this code works for you. I'm trying to get a feel how universal this code would be for the different types of the WS2812 LEDs out there, and also how many LEDs you were able to control with this code. So anyway, thanks for watching. That is how to work with addressable LEDs.